Hi, good afternoon, everyone. This is Alfred Chen. The following talk will be given by Professor Oyama, uh, who is in the NCKU. So, Professor Oyama is a very senior faculty in Japan who participate a lot of rocket and satellite missions. So in this talk, he will give us ideas about the measurement of ionospheric plasma density and the electron ion temperatures. So Professor Oyama, so let's start your talk.
Okay, thank you very much, Professor Chen. Okay, today my talk is the measurement of ionospheric plasma density and electron temperature. Also, I talk about a little bit about ion temperature. This is when I said this ionospheric plasma. This is not only for the Earth's ionosphere. This also can be applied to another planet like Venus and Mars and other planets. Okay, so my talk is stress. This is by famous physicist Kelvin. There is nothing new to be discovered in physics now. Although that remains is more and more precise measurement. So my talk is just concentrate how to get precise measurement. Okay. So now my content is just like this. First, I want to just briefly discuss about ionosphere, what is ionosphere, and secondly, what is still clearly unknown. This is since 1970, we are in the same situation for below 130 kilometer, especially below 60 kilometer. No advancement in this area. Okay, then below 60 kilometer, we call this still ionosphere. Okay, so then third, measurement of basic parameter, which is my main topic today. Okay, then after I talked about the basic principle of the measurement, I'd go to the difficulty and the problem on the measurement. Okay, mainly this is due to the electron contamination. And finally, I just talk brief statement for the future. Okay, so as I mentioned, this is a 90 kilometer chemistry specific. This is what we call it, I have already talked. Then this is the neutral atmosphere. Just I am presenting this in order to give you the rough idea about the atmosphere and ionosphere. If you look at this one, number density on the ground surface, is 10 to 19 particle per square cubic centimeter. Then if we go to 100 kilometer, this becomes 10 to 11 particle per cubic centimeter. That means 10 to minus 7 times less than on the ground particle. Okay, now when we have a neutral particle, because due to the solar UV, these neutral particles are ionized, then become neutral particle. This is the atomic particle or molecular particle. For the molecular particle, sometimes it goes divided into atomic particle, but anyway, neutral particle are ionized by mainly solar UV in low and mid latitude. And if you go to the high latitude in polar region, the neutral particle are mainly ionized by energetic particle, what we call the auroral electrons. So this is put here is the electron density height profile from up to 1,000 kilometer. Usually plasma density at the maximum plasma density around 200, 300 kilometer is 10 to 6, 1 million particle per cubic centimeter. Then if we go to more than 8,000 kilometer, it becomes 10 to 30, something like the electron density. Then at night, the plasma density reduces about 10 times less, one tenth, as you can see this one. Okay. As I mentioned, below 150, this is still, we have quite many things to make clear. This is one I'll talk a little bit later. Then first we have plasma density. Then at the same time, in order to study the ionosphere, we need electron temperature. Ion density is the basic parameter in addition to electroplasma density. So here is T electron temperature, T ion temperature, and the neutral temperature. If you look at around 100 kilometer, neutral particles tend to traverse. On the other hand, plasma density, electron density only tends to hit. So most of the particle around here is neutral particle. Once this is a basic height profile of plasma density, daytime and nighttime, but these height profiles are very much modified by the neutral wind and electric field under the influence of geomagnetic field, Earth's magnetic field. Okay, I'll show you one example. This is the what we call equatorial ionization anomaly near to the geomagnetic equator because of the under the existence of geomagnetic field and during daytime electric field directed to the eastward. Because of this, plasma is just lifted up and flowing along the magnetic line of force. So the real plasma density, this is I think one simulation like this. So Taiwan is, this is geographic latitude. Taiwan is in geomagnetic latitude 20 degrees. You will be somewhere around here in geomagnetic latitude. So Taiwan is good to study this kind of equatorial plasma function. Okay. So next one is topic is what are still unknown, what are still not unclear. Even after 50 years, the situation is the same as in 1970. This time, 1970, 1980, at the beginning of 1980, a lot of satellite sounding rockets were conducted. But still, say, around the height of 90 to 130 kilometers, in the mid-latitude, electron temperature at the around the height of 100 kilometers is much higher than neutral temperature. Neutral temperature is there at the height of around 100 kilometers is usually 200 to 250 degrees in Kelvin. If you look at this number, electron density 10 to 5 electron per cc, neutral density 10 to 12 particle per cc at around 100 kilometers. Then, under this particle number condition, electron temperature should be equal to neutral temperature. There is no way that the electron temperature is much higher than neutral temperature. So this is still unknown. We have unknown mechanism for this one. Although we had in Japan quite many experiments, rocket experiment in the electron temperature. Also, we measured the neutral particle temperature, and another one is what we call vibrational temperature of molecular nitrogen. This combined with this experiment, we now have an idea that this high electron temperature is due to the interaction between vibrationally excited N2 and the electron. When we measure the vibration temperature of neutral N2 nitrogen, the vibration temperature is around 1000 K. much higher than neutral temperature. I think that might explain the this mysterious phenomena. But we have only one rocket to experiment. We need to conduct a further experiment. Yeah. Then another one, the geomagnetic equator and equatorial reactor. This we don't know much about inside equatorial reactor. What is happening? What is the electron temperature? What is the ion temperature? We don't know. Also, sometimes there is the usually electrojet flow from west to east, but some that above that 100 kilometer electrojet sometimes flows from east to west. This we don't know clear mechanism. Okay, so just one mention below 90 kilometer, especially this region is we don't know what kind of ion are existing. The rocket experimented very few. This is the one in Taiwan. Even the Taiwan rocket goes only up to, for the moment, 130 kilometers. You can still do this kind of experiment. Now I go to the measurement of basic parameter, ionosphere parameter. That is plasma density, electron and ion density, and the temperature, electron temperature, ion temperature, neutral temperature. In my knowledge, neutral temperature above, 200 kilometers is well systematically studied by using the air drag of the satellite. Due to the neutral density, satellite, even at the height of 200, 300 kilometers, air is very thick, but still, satellite can be decelerated. Satellite can be decelerated by neutral atmosphere or neutral particle. Then another one is wind in plasma, what we call plasma drift. Yes? So, and another one is composition. This also we have neutral and ionized their particle. Okay, so this I put here is the by blue letters. I will talk about today for the wind. I talk a little bit about the plasma drift equal to the neutral wind. Okay, so in order to get electron density and electron temperature, we use what we call Langmuir probe. This is very simple. This can give us the plasma density, electron density, and electron temperature. Then, if you want to, you can get the plasma irregularity, turbulence of plasma density. Okay, so I first talk about this Langmuir probe, principle of this Langmuir probe measurement. Then I go to retarding potential analyzer. Retarding potential analyzer can measure ion density and also ion composition and wind of plasma, what we call plasma drift. First, let's go to the Langmuir probe. This Langmuir probe theory was established about 1925, long time ago, already about more than 100 years history. But this probe is still being used in the ionosphere satellite, even in the magnetosphere satellite. Okay, the principle like this. This is the plasma around the plasma. If you put any shape of metal. This time is I just put as an example cylindrical electrode. You can put the spherical probe and also planar probe. Okay, if you put, for example, this cylindrical electrode into plasma, first around the electrode, first electron come into the electrode, then later ion follows. This means since this is due to the electron is much higher, electron velocity is much higher than the ion particles. Okay, so principally the electrons becomes negative. Okay, then electron of ambient plasma try to come into here, but because this is electron is negative, electrons are repaired, but ion still come into the electron. This is so there is a region around the electrodes. There is the region where electrons are more than ion. This is what we call sheath. Okay, so we just only the Langmuir probe theory, just to we apply the voltage to the electrode and just measure the electron current. That's all. Okay. In this case, if you go to very negative with respect to the ambient plasma potential, electrode just pull the ion. Okay. Then if you go to slightly going rise this voltage, but still the electrode is negative. Then if you gradually, with respect to the potential, if you gradually increase the potential, first, most of the electrons are repaired. And finally, if the electrode is potential is equal to the ambient plasma potential, whole electron just can reach this electron. This potential, we say space potential. The voltage which applied to the electrode is equal to the ambient plasma potential. This time, we can calculate whole electron density. Okay, so if you look at the, I talk about this one later. In order to apply this Langmuir probe, we need the counter electrode, which is whose area is much larger than the conductive electrode surface. This is a very important factor when you measure the electron density and temperature in space. So then what the curve looks like? Okay, so this is quite typical what we call Langmuir curve. That is a probe current here, which we measure. Yes. Then this is the probe voltage. Okay. I put here is space potential, where this is just probe voltage. We just sweep here from negative to here. As I mentioned, when the probe potential is very negative, we just pick up the ion. This is ion current. Then if we gradually increase the voltage, then electron can reach to the electron. Then the electron potential becomes equal to the space potential. All electrons come into the electron. At this point, we can measure the electron density, for example, per cubic centimeter, something like that. Then from this curve, actually this is exponential curve. Then from this one, we measure the electron temperature. When we say temperature, we always assume the particle are Maxwellian. This is important point. Now we go to the see, as I mentioned before, this is the exponential curve. Here you take the you can see the electron temperature. Okay. Then one example of DC probe measurement. This is in the sporadic E layer. Sporadic E layer appears around 100 kilometer to 10510. Very thin layer, but very plasma density is sometimes 10 to 6 electron, or sometimes 10 to 6 electron per cc. Okay. The principle of the ES layer formation is what we call wind shear theory. Suppose eastward wind go like this, magnetically like this towards the north, and below westward wind. Then ion is influenced by this together, move together with eastward wind, and under the influence geomagnetic field, ion is just accumulate here. Okay, their plasma density something like you can see very very thin layer. Then since this layer is very thin, very difficult to measure the electron temperature, you need a very high resolution DC Lange probe. So that means even now, electron temperature in the ES region is not so many data. Even we don't know, we measure this one, it seems to be electron temperature inside here is very low, maybe close to the neutral temperature. But there is also another report which has been published long time ago, more than 20 years ago. Sometimes electron temperature is higher than the ambient. But this we don't know yet, because we have not confirmed answer to this one, because still measurement of electron temperature inside ES is still not many. Now up to here, I pick up two phenomena. One is equatorial ionization anomaly phenomena over around geomagnetic equator. Even Taiwan is just at the edge of, seems to be at the edge of equatorial ionization anomaly. Of course, this depends on the intensity of electric field. Sometimes if the electric is eastward electric is very intense, the peak of the equatorial ionization anomaly still go to the high latitude. So equatorial ionization anomaly, this is a E cross B drift, and this sporadic E layer is due to V cross B. V actually this I cross B, this is a principal motor. Okay, that I want to say here is all dynamical ionosphere feature can be explained by general university physics. Very simple. If you understand the physics, general physics, you can easily understand the, I think, as long as I know, all dynamic ionosphere feature can be understood. So this is electron temperature. I just want to to show the detail one. So here, electron density, and electron density temperature is just in the antiphase. Okay, here like this. Here is the most dense thing, ES layer, electron density, and we couldn't measure here, just in the midst of ES layer. seems to be very low. Seems to be equal to neutral temperature. So now, so far, I described the very simple Langmuir probe. Then I go to the retarding potential analyzer. What is retarding potential analyzer? In Taiwan also, Professor Chao of NCU, National Central University, put this potential analyzer for almost all Taiwan satellites in my memory. So the principle like this, if you record the Langmuir probe measure both ion and electrons, okay? Then if you can remove the electron, you can get ion cut. The principle here, this is the plate to collect ions in this case. Then in front of the plate, if you put grid, I put the G1, then you put negative potential. Electron will be repelled, okay? But ion just come to here. I put G2, this is just, to repel secondary electron from this plate, because very often retarding potential analyzer move toward the sun, depending on the orbit. Okay, since we are measuring a very, very small current, photoelectron, secondary electron radiated from this electrode due to the UV, we cannot neglect. We need to repair this one. G2 is playing this role. So the amplitude is very simple. Just you measure the current. Also, the current is very small. Okay. In this case, as I mentioned, this what we call retarding potential analyzer can measure ion temperature and ion composition. O2, O plus, NO plus, H2 plus, H plus, something like that. Okay, so the principle of temperature, especially composition measurement, is like that. Okay, in this case, we use the satellite velocity. Okay, usually satellite velocity about 7 kilometers per second, around the height of 100 kilometers to 800 kilometers, something like that. If we go to higher, satellite velocity is less than this, but usually take 7 kilometers per second. Okay, so suppose the satellite just stop there. Suppose satellite is moving with a speed of 10 kilometers per second. From the ion, see the satellite coming to close 7 kilometers. That means if suppose satellite is supposed to stop, ion see this velocity, okay, for O plus, okay, for NO plus, if you calculate corresponding to the 7 kilometers, this becomes 8.2 electron volt. For O plus, this means 4.4 electron volt. This means if you apply about 4.4 electron volt to the first grid, the ion, O plus ion, is like this, cannot go to the electron. Okay, same for the NO plus, if you apply about 8.2, the ion suddenly NO plus suddenly drop to current zero. Okay, where current goes to zero. This square one is we are assuming the ion temperature is zero. So when ion has a velocity or according to their Maxian distribution, this curve also landing like this. Okay. Also, NO plus also goes like this. Okay. So real current go like this. If you put this on this one, real current go like this, then go to like this, go to like this. So from this point, you can get O plus. From this flat point, you can get NO plus. And from this landing, you can get ion temperature. This is the principle of retarding potential analysis. This is one example, the EMSP, American Satellite Defense Meteorological Satellite Program. So this spacecraft routinely launched. This is F-10th spacecraft for this mission. Now I think already more than 16 or 17 F-17. Okay, this is just good example. You can see here. From here, maybe this is O plus. I don't know, this may be H plus, something like that. Okay, so this instrument was first accommodated by Professor Hanson, William Hanson of University of Texas. Now, second follower is Professor Rod Hills. Also, he is going to become very, very senior. And now another third generation is coming up. I forgot his name. So this is the one. I just want to show you the what we can do by just to measure the O plus ion density. Even this can measure the O plus. This is Dynamic Explorer 2, which was launched in 1981. This is retarding potential analyzer measurement. So this one is I want to show you. This is the when earthquake occurred in 1981, October 1906, at the latitude minus 30.1 and longitude minus 30 west of the Greenwich to the west. And this is south of the equator, and this west to the east. Okay, so if you look at the very beginning, I just explained a little bit about. If you look at this one like this, O plus density. This is the geographic latitude. This is just O plus density. Unit 10 to 6 here. Here, like here. This is cross the geomagnetic equator. This is the one I mentioned, what we call equatorial ionization anomaly. Okay, so over the geomagnetic equator, plasma density takes the minimum. But the figure which I show you is the star point with, you can get both sides. Plasma density is higher than this star point. If you don't know the location of geomagnetic equator, you surely think, oh, this might be the geomagnetic equator. But it is actually not. This is over the earthquake center, epicenter of the earthquake. So these things also you can do by retarding potential analyzer. Still, measurement is very, very small because Dynamic Explorer 2 mainly was dedicated to study the polar region. Now, already 10 minutes. Now I go to the difficulty and problem on the accurate measurement. I go to the electron contamination. Okay, so this is still people, scientists, who put the Langmuir probe as a retardant potential analyzer. They were not aware of the serious effect of contamination. Electron contamination means if you put, as I mentioned, Langmuir electrode and just on the surface, there are a lot of contaminant. Mainly, this is the water, and the thickness only 220 nanometer to 80 nanometer. This was the thickness measured in NCKU with the help of some physics department by the Dr. Van Ficken. So if you have a electrocontamination, you see like this. If you increase a bias like this, if you reduce again this like this, you get this kind of hysteresis. This should not be happen to measure the accurate information. If you do that, this is the very clean Langmuir probe, the back and forth bias, the curve should take the same path. So this does not happen if you have electrode contamination. So I don't think I have okay, maybe I think. So this contamination is expressed by very big capacitance and electrode. This is the main cause of this electrode contamination hysteresis. So in order to measure the accurate electron density, you need to remove the effect of this one. Mechanically, I mean, just heating the electrode, you can remove this one, or electronically, you can have a way to reduce this effect. Okay, so if you have this kind of hysteresis, electron temperature is much higher than this, electron density much lower than this. Okay, because electron density is, if this one low and electron temperature is high, again electron temperature is estimated much lower than the real one. This is very much happening in the current satellite project as well. So this is for the retarding potential analyzer. If you do the experiment in chamber, this is chamber which I did the long time. Still, you can measure the, you can get this kind of hysteresis. Okay, for retarding potential analyzer, the effect of electron contamination is much less than the single electron, but still you will see the hysteresis. This should be taken into account depending on the atmosphere before you launch. Hysteresis become bigger than this. Okay, so the before the launch, we need to take care of the how clean the electrode surface, especially for retarding potential analyzer. Okay, so another problem, I think I'll go slightly going to the conclusion. Another problem, small satellite mission. Okay, this is now we are going into the CubeSat era. Okay, now time is coming for CubeSat mission. The big problem of CubeSat when we use the Langmuir probe is the conductive surface of the CubeSat. Okay, in order to work for the DC probe work, we need, for ideal case, we need 1,000 for the area ratio of electrode surface and conductive satellite surface. So here is, if we change this, and this is again was calculated by NCKU student long time, almost 10 years ago. Okay, this is the one. 100. Suppose the ratio become surface area become 110. Then compared with 1000, it gets like this. About 1/3 of the current you get. So you cannot get the exact number. For the CubeSat, I think the conductive surface is much less than 400. Then what happens if the conductive surface area becomes not enough? Okay, so this is the one, and this is the CubeSat. We have a sheath, as I mentioned, surrounding the satellite, and we have a here is the satellite frame. Satellite frame. We have a just on the satellite frame. We have again conductive and contaminating surface, and this is the sheath, and this is plasma. Then current go back to like this. Again, this electrode. At the electrode, we have a sheath, and again we have a contamination, resistance and capacitance. We are measuring this one. Then what is happening? This one. Okay. What happens if we have a very small surface area? If we want to apply for the greater to 3 volt, real electrode potential, which you apply to become less than 3 volts, okay? Then instead of become less than 3 volts, satellite potential is going to negative. This is happened. This is one thing. So at this moment, you cannot get the accurate electron density. What about the, this is probe current. Here is when the electrode is ground. If you use the electron contamination electrode, this go like this, okay? If the, electrode is the CubeSat, go like this. The current is small. This is due to this effect. The conductive surface area of CubeSat is much smaller than the conventional satellite. So this is, again, was conducted by my previous student in NCKU. Okay, so this is end of my talk. For the future, what I discussed here is not only for the our Earth ionosphere. This problem is also common to the measurement up to another planet like Venus or Mars. This is the electron contamination. So that I would like to always stress. We need to make the maximum effort to get accurate data because rocket and satellite mission is expensive, time and energy consuming. Okay, thank you very much. This is end of my talk. Thank you very much for listening.
Okay, thanks for the talk. I just get back for the reception. Okay. Is there any questions from the participants? Is there any questions from our participants?
There is. I wonder, a couple of years ago, someone proposed atmospheric studies for weather patterns with essentially hundreds or thousands of femtosatellites. That's something like much smaller than the CubeSat and more like a chip card or a credit card. Imagine like that. And the idea there was to essentially have many of those sensors and drop them into, well, I guess you could say something like a typhoon, and then get accurate atmospheric measurements through those little chiplets. I wonder, I mean, you're trying to study something here, or you want to propose to study something here that's roughly in a very low Earth orbit.
Low Earth orbit?
Mm-hmm.
You mean the satellite?
Yes. So I wonder if it would be possible to get your kind of data that you're looking for with something that is smaller than CubeSats.
Satellite. But you know, satellite is below 200 kilometers.
Yes.
Because of the air drag, it's not cost effective. One thing.
Yes.
Okay?
Yes, exactly.
And another one is satellite mission. Very mission period become much shorter.
Yes,
if
that's
you
why.
go below 200 kilometers.
This is the exact reason why some people have proposed to use femtosatellites, so much smaller satellites than CubeSat.
Oh, that in my opinion, I don't agree with this proposal because mission life is very small, and if you go to below 130 kilometers, if you want to measure the aerodynamic drag, aerodynamic heating, is very high. If you look at the modernizing the satellite velocity, if you fly around 130 kilometers, the satellite velocity more than 7 kilometers per second. Okay, if you put this number to the, convert to the temperature, neutral temperature, that becomes more than 3,000 K. Okay, so you cannot continuously measure the low altitude like 130 kilometers. It's not. It's possible, but a very short time. It's not cost effective.
So, yes, that's okay. Because of exactly this problem. People have proposed to use very low mass, very high surface devices that are then very light, so your temperature stays low.
Yeah, but still, you know, it's amazing. The aerodynamic heating is very strong. So most of the metal will also melt down below 130 kilometers.
Okay.
So one way is in the past, only atmosphere explorer C went down to, I think, 140 kilometers. Okay. This case, satellite had the very much long eccentric orbit. Just very foreshine, went down to 140 kilometers, then go up. This is a repeating. That can be done because very short period around the height of 140 kilometers, you can measure. This is, did I answer to your question?
Yeah, it follows it along a bit. So yes, thank you very much.
Elliptic orbit.
Yeah, cool. Thank you.
Yeah, low orbit, maybe 100, maybe you can try 130 kilometers, very for a short time, and then go up to very high apogee. That can be done.
Now, the idea for those atmospheric study missions was essentially not really to be in a permanent orbit or in a long-lasting orbit, but the idea there was essentially to just drop through the atmosphere slowly and maybe to have a lifetime of several days.
Just so this is only one drop. I mean, maybe.
Yeah, that's only one. Essentially, it's more like a drop, less like an orbit. Okay. Imagine taking a pillow with feathers and opening it and letting the feathers fall.
That, from my opinion, like this, only one data is not enough. Even 50 sample at the same time.
Yeah, you would get thousands.
To study is very difficult to publish a paper, in my opinion.
Yeah, you would essentially need thousands of these chiplets.
Yeah, but again, become very cost effectively not, I don't think.
Okay.
Thank
you for your thoughts.
This is my personal opinion. Okay.
Okay, is there any other questions from participants? Okay, if no further questions, so let's thank our speaker, Professor Oyama, for his great talk. Okay, thank you very much. Professor Oyama.
Okay, thank you very much. Okay.